So let's review some of the notes for series and parallel circuits. A series circuit is a circuit that has a single pathway for charges to flow through. When I say single pathway, what I mean is looking down here at the bottom of our paper. If I start at one point on that circuit and I try to trace it, there's only one way that I can get around that circuit from beginning to end. So that would be a single pathway. What we've seen in our labs and through our data collection is that as we add more and more components to a series circuit, it increases the overall resistance. So by adding more light bulbs or by adding, plugging more things into a series type circuit, that resistance starts to increase. And based off of the relationships we have from Ohm's law, we know that as resistance increases, the current begins to decrease. So as we add more components, our total resistance will increase, which will result in a total current decrease. In our labs, we saw that that total current decrease also led to a decrease in the overall power, whereby the light bulbs that we witnessed in the digital lab were dimmer and dimmer and dimmer each time that we continued to add. Ultimately, at some point, if I added enough light bulbs, the resistance would become so great that the current would not be able to flow and the circuit would no longer run. We also saw in our digital lab that the voltage was split up through across the different components that were plugged into the circuit. In some cases, the voltage was split up equally amongst the different resistors, but in other cases, we saw it was not equal. And so the amount that the voltage is used is going to depend on the size of the resistor. We should remember from Ohm's law that there is a direct relationship between resistance and voltage. So the larger that the resistor is, the more of the voltage it will need in order to be able to push the charges through that circuit, through that component. The last thing that we witnessed in the lab was that because there was only one pathway for the charges to go around, the current was constant. It was equal throughout the circuit the entire time. So however many charges left my battery down here had to go through, they all had to go through this resistor. They all had to go through the next resistor. They all had to go through the next resistor. So at any point along that path, the resistance would be the same as it was at the beginning. Okay, that's following the law of conservation of charges that we looked at in our previous units. As a result of recognizing that that current is constant or current is the same, our third and final equation for series circuit is recognizing that the total current will equal the current through the first resistor, through the second resistor, so on and so forth. If there were 10 resistors, they would all still be equal. So down below, we're going to be able to look at how these equations relate to the math that we have. I'm going to go ahead and zoom in on what we have down there, but I'll keep referring back to these equations up above. So this is a series circuit, and again, we recognize that because there's only one pathway to get around the circuit. At no point are we having to make a choice. Being as it is a series circuit, we should recognize right away that the total current will be constant the entire time. So once we can identify that current in one place, we'll know it from there on out. Other information that I can pull off of the diagram itself is that the total voltage is 12, our total resistance is 60, the resistance of the first resistor is 27, and at the second resistor, 15. I tend to use a table, and if the table is not given to me, I tend to draw a table so that I can identify areas where I have the majority of the information. So by looking at this table, I can see that I have 1, 2 of the 3 components that I would need in order to complete that first column. Or I can see that I have the majority of the information that I would need to complete this final row down here. So I would probably want to start solving the rest of my circuit by either identifying the total resistance or identifying the total current, or by identifying the third resistor. To identify the total current, I am going to go back to one of our old equations, our Ohm's law equation, where we know that V equals I times R. So if my voltage is 12, I'm looking for my current, my resistance is 60. By rearranging my equation, I'll see that I need to divide by 60 on both sides. 12 divided by 60, my current will be 0.2. So that's my total current that leaves the battery. Now remember that the total current is conserved or is constant in a series circuit. So I'll also have 0.2 amps traveling through the first resistor. I'll have 0.2 amps traveling through the second resistor, 0.2 amps traveling through the third resistor, and 0.2 amps returning back to the beginning of that circuit. In order to solve for the resistance down here, the next area that I have the majority of that information, I'm going to apply the equation from up above, where the total resistance is equal to the first resistor plus the second resistor, so on and so forth. So 60 is 27 plus 15 plus our missing R. 27 and 15 gives me 42. And so rather than adding to get my R, I'm going to subtract. So 60 minus 42 will give me my missing R, a value of 18 ohms. To finish solving, the next things that I have is I can see that I have current and resistance for each of these parts, and so I should be able to find my voltage. So in order to do that, I am going to again apply Ohm's law. So I'm going to do V equals I times R. So 0.2 times 27 will give me my V. 0.2 times 15 and 0.2 times 18. So 0.2 times 27 should give me 5.4 volts. 0.2 times 15 should give me 3 volts. And 0.2 times 18 should give me 3.6 volts. Now there was a lot of steps involved here, so I always suggest to my students that they verify or double check their answers. Since the last thing that we solved for was this voltage row, I should be able to double check that information and make sure it holds true. Recall that we said the total voltage should be used throughout the circuit. So our first voltage, our second voltage, and our third voltage should add back up to that total. So I want to verify that 12 is in fact 5.4 plus 3 plus 3.6. So if I add those in my calculator, I see that 5.4 plus 3 plus 3.6 is in fact 12, and so I've been able to double check my answer. Since this was the last thing I did, if it holds true, then the probability is that I hadn't messed up on any of my other work. So next we're going to look at parallel circuits, and the difference between series circuits and parallel circuits is that a series circuit was only a single pathway, whereas a parallel circuit is made up of many or multiple pathways. So with the drawing test, if I start at my battery and I try to trace my circuit, by trying to trace my circuit, I can only get through one piece of that circuit in a smooth path. I've missed all these other points. And so that tells me right away that this must be a parallel circuit because it has at least two pathways. In a parallel circuit, what we saw was that by adding more components to that circuit, each time we add a component, it adds more pathways. And this is like adding more lanes to a highway. By having more pathways, we're actually able to decrease the overall resistance. There's less congestion through those different circuit components. And as a result, our current is able to increase. Again, that's that inverse relationship we saw earlier. So we see that drop in the overall resistance, which gives us an increase in that overall current. And as we discussed, current is directly related to power, so we'd also see an increase in the overall power. As a result, light bulbs or other components that are connected in a parallel path will tend to have more power being drawn through them, which would make our light bulbs brighter. Potentially they'd run a little bit faster, slightly more efficient. The equation for solving for resistance, because we need to decrease that overall resistance, we're actually going to add the reciprocals, or the inverses of those resistors. So to do that, we can use the inverse button, or the x minus 1 button, on our calculator. Now it's important to make note of the fact that according to this equation, the answer that we come up with is also going to be a reciprocal. So to finalize our answer, we will need to take the inverse of the answer that we get from adding those different components, and then we will have our final answer. So I'm essentially taking the inverse off of here, bringing it over here in order to be able to cancel it out or to balance it. Let's look at we'll look at what we mean by that in our example down below. Now, in a series circuit, we said that the current was constant, but in a parallel circuit, the voltage is constant. Each branch is going to be provided the same amount of potential voltage, so that each branch can work as effectively as the other branches, regardless of whether there are components attached to it or not. And then the last rule that we were able to see is because there are multiple pathways, there's different options for the current to go. So the current is actually going to split up. There'll be more current that passes through branches with less resistance. But as a result, we should always maintain the same total amount of current. If I started out with 3 amps of current and 2 amps went down one branch, that would mean that 1 amp had to continue along its way. By the time they get back to the end of the circuit, I should have all 3 amps back together. So this 1 amp would join back on at this junction, and from there on I'd have my 3 amps. I'd maintain my total current following that law of conservation of charge from before. So let's go ahead and look at an example problem down below. I'm going to go ahead and zoom in. So just like before, I do suggest working with something like a data table. And as we said earlier, we identified that this is a parallel circuit for the fact that it has one branch here and a second branch here. So having at least 2 branches makes it parallel. In parallel circuits, the voltage is constant across each branch. So every branch should maintain the same amount of voltage to work equally effectively. On the side, we see that there are 12 volts coming from the battery, which means that there are 12 potential volts applied across the first branch and 12 volts applied across the second branch. Other things that have been given to me is that my first resistor has a value of 2 ohms and my second resistor has a value of 6 ohms. So from here, just like before, I want to try to identify areas that I have the majority of the information. So I could start out by working down where I have voltage, current, resistance, and I can apply my Ohm's law. Or I can work across the bottom where I have 2 resistors and could use that to find my total resistance. Since we're a little new to the equation, I'm going to start out by using this blue one, where my total resistance and my 2 components. So the equation from up above is that the total resistance, or the inverse of the total resistance, is equal to the inverse of the first resistor plus the inverse of the second resistor. And if I had more resistors, I just keep adding. So 2 to the negative 1 plus 6 to the negative 1 will give me a total to the negative 1. So to do this, I'm going to type this in my calculator. 2 to the minus 1 plus 6 to the minus 1. And again, that minus 1 is coming from the inverse button, which can be found right above the 7, and that will give me that inverse value. So if I do 2 to the minus 1 plus 6 to the minus 1 and I hit equals, in my calculator I'm going to get 0.6 repeating. Now remember, this has an inverse on that total. So I want to take it and apply it to my answer in order to be able to cancel it out, to get rid of it. So my total resistance is actually going to be the inverse of 0.6 repeating. So on my calculator, I want it to say the inverse of the answer. I can do that by simply pushing that x minus 1 button again, and it should show on the top of the screen answer to the minus 1. When I hit equals, that tells me that I actually get 1.5 ohms as my resistor. Now, it's not overly important that you understand the math behind it, but for those of you who are interested, what we're getting here is an inverse or a reciprocal is really kind of like fractions. So my total resistance is equal to 1 over the second resistor and 1 over the other resistor. And so to solve fractions, I'd have to find a common denominator. So a common denominator would be 6. So I can do 3 over 6, that's still half, and 1 over 6. And so I'd add those together to get my 1 over that total resistance. So 3 plus 1 is 4. Denominators were both 6, and that gives me 1 over my total resistance. Now, I want the total resistance to be on top, so if I flip this side, whatever I do to one side, I have to do to the other. I'd have to flip this side, meaning that my total resistance over 1 is actually equal to 6 divided by 4. And if I type 6 divided by 4 in my calculator, I get 1.5. So that's mathematically the logic behind that inverse button. Again, you don't have to be able to work in fractions because we have the inverse button on the calculators, but if you don't have a calculator or if you like fractions, then you are welcome to solve it this way as well. So now we have the voltage and resistance for all 3 of our component pieces. So it should be pretty easy to solve for the actual current, the I. To do that, we're going to use our Ohm's law equation, V equals I times R. Now we want to get I by itself, so I'm going to divide by R on both sides, and I'll find that I equals V over R. So for my first resistor, I'm going to do 12 divided by 1.5, and that will give me my first current. So 12 divided by 1.5 is a total of 8. Can do the same thing for my next for the first resistor, pass the total. So 12 divided by 2 is going to give me a total of 6 amps. And 12 divided by 6 for my last resistor will give me 2 amps. Now, as a way to verify that I have completed my math properly, what I can do is actually use that last equation that we did in our notes, where the total should equal the first one plus the second one plus the third one, or however many I have. So 8 should equal 6 plus 2. Since 8 does equal 6 plus 2, it's a quick way to verify that I've done my math correctly. So we're starting to see that the basis for circuit calculations comes from the Ohm's law equation, V equals I times R, or rearranged as I equals V divided by R. We'll also be working back towards our power equation from the previous unit, where P equals I times V. And then, of course, our resistance equations. So for a series circuit, we're simply adding up the values of those resistors. For a parallel circuit, we're going to be adding the inverses. So using that -1 button on our calculator. Beyond that, it's important to start working on memorizing the patterns. So remembering that in series, the current is constant and the voltage adds back to the total. And remembering that in parallel, the voltage is constant, and it's the current that adds back to the total. It's very important that we start to learn these rules over here, because without those rules, it makes it very difficult to solve the rest of the pieces.